During this model, we'll be talking about additional aspects of aqueous equilibrium. After this model, you will be able to describe the common ion effect. Also, you will explain how a buffer functions, and you'll be able to calculate the pH of a buffer solution, and also calculate the pH of a buffer after the addition of small amounts of a strong acid or a strong base. And finally, you will calculate the appropriate quantities to make a buffer at a given pH. So let's talk a little bit about the point of equilibrium that we talked in the previous model. And let's see the effect of acetate on the acetic acid equilibrium. The acetic acid equilibrium is basically you have this weak acid, acetic acid here, and at equilibrium it will produce a proton because it's an acid, and an acid will give a proton, and you will have the conjugated base that in this case is the acetate. Okay, so this is the equilibrium of acetic acid, will produce a proton plus the ion of acetate. If we add to that equilibrium a solution of sodium acetate, which is a strong electrolyte, we will add this sodium acetate. The sodium acetate is soluble in water, so it will be dissociated to sodium and acetate. So if you add sodium acetate to this equilibrium, you will be adding also the ion of acetate. And this acetate will increase the concentration of this acetate in equilibrium. So it will be affecting the equilibrium, and this will shift the equilibrium to which side, the left or the right side. If we are increasing this concentration, we will like to decrease that concentration to reach equilibrium again, so that we'll shift the equilibrium to the left. So the presence of the acetate from sodium acetate in an acetic acid solution will shift the equilibrium according to Le Chatelier's principle. Okay. So this is also known as the common ion effect, because in the equilibrium you have acetate and you're adding a common ion that is in the equilibrium. So whenever a weak electrolyte and a strong electrolyte containing a common ion are together in solution, the weak electrolyte ionizes less than it would if it were alone in solution. This will also affect the acid-base equilibrium, and also will affect the solubility of that acid in equilibrium. So let's see an example of an acid base and the ion effect. What is the pH of a solution made by adding 0.3 moles of acetic acid and 0.3 mole of sodium acetate to enough water to make 1 liter of solution? Number one, we have our equilibrium of acetic acid. Now, before we saw an example like this, but the products, the initial concentration of the product were 0. In this case, because we're adding acetic acid, that is this one, and we're adding also sodium acetate, that is this one, our initial concentration of sodium acetate is not going to be 0. Okay, it's going to be 0.3. So the initial concentration for acetic acid, actually the Ka, sorry about that, the Ka of this equilibrium is equal to the concentration of the product. That will be the concentration of protons times the concentration of the acetate divided by the concentration of acetic acid. And this will be equal to 1.8 power of 10 powers minus 5. This is the Ka. So we want to know the pH. To determine the pH at equilibrium, we need to determine the concentration of H positive, because pH is equal to minus log the concentration of H positive. So the initial concentration for acetic acid is 0.3 molar. Is 0.3 moles divided by 1 liter is 0.3 molar. For the proton, we don't have initial concentration of the proton, but for the acetate, we have 0.3 molar of acetate, okay, because we are adding that concentration of sodium acetate to the equilibrium. Now, the change in concentration, we don't know which one is the change. So if we don't know, it's X. So for the acetic acid will be minus X, because this is the reactant, and the reactant is consumed during the reaction. For H positive, the concentration of proton will be plus X, as well as for the acetate. That means that at equilibrium, the concentration of the acetic acid will be 0.3 minus X, the concentration of the proton will be X, and the concentration of the acetate will be 0.3 plus X. So now we can use this concentration, these expressions, and substitute in this Ka to determine the concentration of H. And that's what we're going to do in our next slide. So here we have the 1.8 times 10 power minus 5, the X, that was the concentration of H positive at equilibrium, 0.3 plus X, this is the concentration of acetate at equilibrium, and also the concentration of the acetic acid at equilibrium. Now, we can assume that because this is a weak acid, we can remove this X, okay, we can discard that X, because it's pretty small. The acetic acid is really a weak acid, and by doing that we can simplify our equation, and now 1.8 times 10 powers minus 5 equals to X times 0.3 divided by 0.3. So that means that our concentration of H positive is 1.8 times 10 power of minus 5. So now the pH will be the minus log of this concentration. That is minus log of 1.8 times 10 minus 5 powers minus 5, and the pH will be equal to 4.74. Buffers. Solutions of a weak conjugated acid-base pair that receives drastic changes in pH are called buffers. These solutions contain relatively high concentration, 10 power of minus 3 molar or more, of both the acid and the base. Their concentrations are approximately equal for both, for the acid and for the conjugated base. So there are two different ways that we can prepare a buffer. One of them is to mix a weak acid and a salt of its conjugated base, or a weak base and a salt of its conjugated acid. So if we have the acid and the salt of the conjugated base, we can mix them, or if we have also the weak base and the salt of the conjugated acid, we can mix both reactants and produce a buffer solution. Also, we can add a strong acid and partially neutralize with a weak base, or add a strong base and partially neutralize a weak acid. In that way also we can have for example, in the first part, the strong acid and the conjugated base, or the base and the conjugated acid. So in both of the ways, you're going to have the acid-base pair, conjugated pair. So how a buffer works. Here we have a buffer solution of HF and also of fluoride. The concentration of both is equal. Okay, so we have here, this is the acid, it has the H, and this is the conjugated base. Sorry. What happened if, for example, we add base, any base, OH, strong base. This base will react with whom? With this or with this? Because this is a base, it will react with the acid. Okay, so in that way, it's going to produce H2O plus fluoride. Okay, so this HF will react to that amount of base that we added, okay, and will produce H2O and the ion of fluoride. So that means that the concentration of HF will decrease because it reacts with OH, and the concentration of fluoride will increase because that's a product of this neutralization of this OH with the acid of the buffer. So here we have that expression, or the result of that addition of OH, decreasing the concentration of HF and increasing the concentration of fluoride. So the presence of HF also counteract the addition of a base, and the pH will increase is small. Okay, so it's the increase of the pH is really small. It's not that dramatic. So going back here again to the buffer solution, if we add now an acid, this acid will react with whom? With the base or with the acid? An acid will react with the base, so it will react with F, and it will produce HF. So that means that the concentration of fluoride will decrease and the concentration of the acid will increase. And that's what we can see here. And the same way, the presence of the fluoride counteract the addition of the acid, and this decrease in pH will be also really small. It's not going to be that dramatic. So adding a small amount of acid or base only slightly neutralize one component of the buffer. So the pH doesn't change much. So what can we calculate the pH of a buffer? I'm going to show you here how to find out an equation that we're going to use a lot. Is known as the Henerson-Hasselbach equation, and I'm going to show you how to do the derivation of it. You don't have to learn all the steps, but at least at the end you need to familiarize with the last equation. So let's start with our acid dissociation constant. Okay, for a weak acid, we know that Ka is equal to the concentration of the products divided by the concentration of the acid. And if we apply the minus log to each side, we're going to have something like this. Okay, minus log of Ka equals to the minus log of H positive and the minus log of all this expression. The minus log of Ka will be equal to what? Actually, before that, let's just rearrange this and put the log of H outside and move the log of Ka close to this expression. Now we have this, and now the minus log of the concentration of H positive is pH, and minus log of Ka pKa. So this means that this equation is equal to pH equals to pKa plus the log of the concentration of the base divided by the concentration of the acid. This is known as the Henerson-Hasselbach equation. This equation will apply only just to buffer solutions. So let's do an example. What is the pH of a buffer that is 0.12 molar in lactic acid and 0.10 molar in sodium lactate? The sodium lactate, this lactate is the conjugated base of the lactic acid. Okay, so we have here the concentration of the acid, and we have here the concentration of the base. We have the pKa, we have the Ka, but we can determine the pKa, so we can substitute the values in the Henerson-Hasselbach equation. We need to determine the pH. The pKa will be equal to the minus log of this value, and this will you will add the log of the concentration of the conjugated base, that will be 0.1 molar, and the concentration of the acid, that will be 0.12 molar. So here we go. The pKa minus log of this equation, this constant, the Ka, plus the log of the concentration of the base, a conjugated base that is lactate, the concentration of 0.1 molar, and divided by the concentration of the acid, that in this case is lactic acid, it is 0.12. So this will be equal to 3.85 plus minus 0.08. So the pH for this buffer solution is 3.77. Now let's talk about the buffer capacity. The amount of acid or base the buffer can neutralize before the pH begins to change to an appreciable degree. That's the buffer capacity. Using the Henerson-Hasselbach equation, the pH will be the same for a conjugated acid-base pair of 1 molar each or 0.1 molar each. However, the buffer, which is 1 molar, can neutralize more acid or base before the pH change. So as long as we have the same concentration of the acid and the base pair, the effect of the adding more acid or base, it will be the same as if it was a higher concentration of that acid-base pair. But the ones that has a higher concentration can neutralize more acid or base than the one that has lower concentration of the acid and base conjugated pair for that buffer. So now let's talk about the pH range of a buffer system. The range of pH values over which a buffer system works effectively, that's a pH range. The optimal pH for a buffer solution is where the pH is equal to pKa. and that is when the concentration of the acid is equal to the concentration of the conjugated base. Okay, so the optimal pH is where the pH is equal to pKa. If one concentration is more than 10 times the other, the buffering action is poor. This means that the pH range of a buffer is usually plus minus 1 pH unit from pKa. So for the previous example of acetic acid, the pKa was 3.85, a buffer solution of acetic acid. The range uh, that for the system to work effectively will be from 2.85 to 4.85. That's pH range for this buffer to work effectively against any drastic change, because adding a strong acid or strong base to that buffer. So now that we have understand the concept of a buffer solution, um, let's see what is going to happen when you add a strong acid or strong base to the buffer. Remember that the buffer has a weak acid and the conjugated base, or a weak base and the conjugated acid. So you have both species in that buffer. So when you add a strong acid, that acid that you're adding is going to react with the base that you have as in the buffer. And if you're adding a strong base to a buffer solution, that base is going to react with the acid part of the buffer. So adding of the strong acid or base is a neutralization reaction. You are neutralizing that species of acid or base with the buffer. Calculate like stoichiometry problem to find the concentration of HA and A minus, and when all of the added acid or base react. So that's the first part that we're going to do. So we're going to determine what is the final concentration of the species that are part of that buffer that result due to the reaction with the strong acid or strong base that was added to the system. And then when we find that those concentrations, then we can use the Henerson-Hasselbach equation to find the pH of that solution. So here we have the buffer, okay, where you have the acid and the conjugated base. If you add a strong acid, the strong acid is going to react with this base and it's going to change the concentration, because it's going to reduce now the concentration of A minus because it's reacting with that acid. And also you're increasing the concentration of HA. So we need to use the Rise table to find these values. And then when we have this, we can substitute in the Henerson-Hasselbach equation to obtain the pH. The same concept if we have the buffer and we add the strong base. The base is going to react with HA, that is the acid in this buffer, and you're going to have A minus. So you're increasing now the concentration of A minus and decreasing the concentration of HA. So we need to calculate those new values, okay, after that neutralization reaction. And then with these values obtained, we can use the Henerson-Hasselbach equation to obtain the pH of the solution. So let's see this example. We have a buffer that is made by adding 0.3 moles of acetic acid and 0.3 moles of sodium acetate. The acetic acid is the weak acid, and the acetate is the conjugated base. Okay, this is the acetate here, sodium acetate. To enough water to make 1 liter of solution. Calculate the pH after 0.02 moles of sodium hydroxide is added. So here we have hydroxide. Hydroxide is a strong base. So this base is going to react with the acetic acid that is part of that buffer solution. Okay. Also, we can see here that 1 OH is going to react with 1 acetic acid. So that means that the stoichiometry is 1 to 1. So we have enough of this acetic acid to react with all of this sodium acetate and neutralize this hydroxide effect. Okay, so before the reaction, we have acetic acid. The concentration is 0.3 molar. Remember that is mole divided by the volume, that is 1 liter. So 0.3 molar. From the hydroxide, we have 0.02 molar, and the acetate we have 0.3 molar. So remember that the purpose of the buffer is to avoid that dramatic change in pH when a strong acid or a strong base has been added to the system, and they do that by consuming all those strong acid or strong base. So the idea here is to consume all of this. So that means that the change must be minus 0.2, okay, because we need to consume all of this. So this is gonna react with this, so that means that you're gonna subtract also 0.02 of this, but also you're gonna consume this, but you're gonna produce acetate because you're consuming now 0.02 of the acetic acid and produce 0.02 of the acetate. So after the reaction, we're gonna have 0.28 of the acetic acid, 0 of the hydroxide because it was consumed by the buffer, and 0.32 molar of the acetate. So we have the concentration of the weak acid and the conjugated base. So we can use these two values in the Henerson-Hasselbach equation. And now we also know the pKa of acetic acid. So since this is a buffer, the volume for each concentration is the same. So the ratio of molarity can be calculated using also the ratio of the moles, okay, because it's the same volume. So the pH is equal to pKa plus log the moles of the acid divided by the moles of the conjugated base. And this will be equal to 4.74 plus the log of 0.32 divided by 0.28. So this is the acid and this is the base after the neutralization of OH. And as you can see here, the system was at 4.74, and after the adding of the strong base, it was 4.8. So the difference is basically 0.06 units. So here we have the buffer, pH 4.74. The buffer is in water. Okay, so here we have water plus the acetic acid and also the sodium acetate. And to this system, we add the sodium hydroxide. And as you can see here, the pH changed from 4.74 to 4.80. Okay, so the pH increased basically 0.06 units. So what happened if we have just water? If we have just water, the pH of water is 7. And when we add the OH, the pH increased to 12.30. So the pH increased 5.3 pH units. So this is the importance of a buffer system because it will avoid this huge difference in pH by the same amount. You can see here that we adjust the same amount of sodium hydroxide to both systems. This one has a buffer, this one is without a buffer. And we can see here that the buffer really protects that dramatic change in pH. And this is really important for some, for example, biological systems as for the blood, that we need to keep this 7.4 pH in the circulatory system. So the acid-base buffers are really, really important.